reducing the thickness or changing the cross-section area of a long piece by compressive force. Rolling is the rollers applied through a set of rolls, not necessarily two, but it can be multiple. It is similar to rolling and rolling dough with a rolling pin to reduce its thickness. If you have done some cooking work at home and you do know this is rolling dough using the rolling pin. So we have the plates, okay? Plates and sheets. The plates, usually when we talk about plates, we mean the workpiece thickness is decently big. The sheet, this is a 6 millimeter. This is very thin. So this generally regarded as having a thickness greater than 6 millimeter. I don't know why they use 6 millimeter as a threshold value. We just know. Okay, so this is empirical. This is no any scientific. This is the lying principles why this 6 millimeter is used as a threshold value. But we just know for this is a community. If the place is thickness is higher than 6 millimeter, and we treat it as a plate, and otherwise we treat it as the sheet. So this is the thin sheet. So these are structural applications such as boilers, bridge, gutters. This is for the civil engineering application, ship house, and the machine structures and nuclear vessels. So these are plates is big enough. The sheets, and they are usually for the automobile bodies. Automobile body is not very thick and it is thin. Also, the aircraft fuselage and the office furniture. And you can see, look at this is a furniture, if we have some sheets or not. Plants at home, and also food and beverage containers. So we have plates and sheets, right? So these are rolling operations. So rolling operations, we have this is continuous. We might have continuous casting of ingots to the workpiece. We just get raw material. And we have slab, and we have the billet, and we have group with different. And different slab has several. This is the hot strip, scalp, and plate. And for this billet, we have hot rolled bars. These are rolled bars you can see. The bars is coming out, and the cold drawer bars. And so these are rods there. The wear and wear products, and these are two rounds. These are two, and this is seamless pipe. And also this is bloom and structural shape. Because structural this is I-beam. So this is a real application. So you can see different applications, and we will use different operations. So this is a big industry. So in US, this is a big industry. So by the way, Dr. Arif Malik, he is an expert in the metal forming processes. So he left through and moved to the University of Texas in Dallas. And then we look at this hot rolling. For this hot rolling, so this is the ingot, the wood piece. So this is a hot rolling means that we elevate the temperature. So here is a roller. This is one roller, and without loss of generality, we only use two rollers here. Right? So this is one roller. This is one roller, and these two rollers. This is a counterclockwise. This is a clockwise. I'm sorry. This is the clockwise. This is the counterclockwise. These two guys are rolling in opposite direction. So here is a billet. Here is ingot. This is a wood piece originally, and we can. This is original. This is the grain size. So we can call this is equal X. This is the grains. But out, we compress it. You can see. So this is the dimension, and in this y direction is reduced substantially. So all these grains, and they are not equal X the grains anymore. So here is this elongated grains. So this is a new grains forms. A new grains growing. So these new grains growing. So this recrystallization are complete. So recrystallization means that they have the different. They have another different grains from here to here. So this is deformed, elongated grains. So this is deformed. So definitely we have applied works there. So this is just with a fine grain size and improved property. So this is the hot rolling. And hot rolling usually need more more expensive equipment to do it. So this is effective way to reduce spring size. We can reduce the spring size. This is the original spring size. This is the final spring size, and we can refine the microstructure in metals and resulting in improved strength and good ductility. So this is very, very good. So in this process, cast structure of ingots or continuous castings are converted to rod structure. So this from casting cast structure to this is rod structure. This one can be used can be used to sell, can be sold. So then we look at mechanics of rolling. Mechanics, even though it is automated, if this is automated, however, if we just take a look at this guy and just draw the free body diagram, we can know on how it works, and from the perspective of mechanical engineer students, from the perspective of mechanics person. So here's a roller, and here is another roller. Here is a roller. We just without loss of generality. We have this is V0 here. So this is initial speed, and this is final speed. And so this roller is rotating at the speed of VR. Right. So here is the speed. This is the speed, and V0. This is the VR, and this is the VF. So we have original width. So this is the final width. So this is the velocity here. VF is here. And initial thickness, and this is the final initial height. We say the initial height, and this is the final height. So this is roller, and this is the top row is removed just for the visualization purpose. Right, so this and forward slip, we can have the final speed minus this is the final speed minus the VR and divided by VR. So this is the forward slip. So sometimes there is a slip. So to the left of this point, the row moves faster than the workpiece, and to the right, the workpiece moves faster than the row. So this depends on where the point is. This is mechanics. You can take a look at this mechanics. So here, if we do the free body diagram, you can see. Okay, so this is the infinitesimally small. This is a wedge. This is a trapezoid. So for this is entry zone. This entry zone, and we have this is a pressure here, right? This is pressure given by the roller, and also here definitely there is a friction. So this is suppose this is the sigma x plus d sigma x. Here is the sigma x. So here is h plus dh. So this suppose this h. And so this is h plus dh. So this is for entry zone. For the exit zone, right? For the entry zone, the friction, and because this guy is entering the roller, the gap of the roller, so the friction goes in this direction. But for this one, because this guy is exiting this the gap. This is the gap between the roller. So here is a friction. It's a different direction, but this row, the pressure is the same in the same direction. That is perpendicular to the surface. So we have this is the sigma plus d sigma x. This is the sigma, and we can, if you are interested, and you can derive this is based on the force balance equation, and you can just derive these equations from the scratch. Right? Scratch means that from the force balance equation. So in this direction, that means in the x direction, all the forces must be balancing one another, and in the y direction, all the forces must be balancing one another. If you use these two equations, and you can get this pressure, and this entry zone pressure, this is P, this is P. Right? So this can be written as YF prime. YF prime is yield strength. H is the height. H0 is is initial height. E mu is the friction coefficient, and this is H0 minus this H. So the exit zone pressure can be using as this equation. So this H is given using this equation. See, this H is related to the R and HF. HF is the final height. R is a roller. R is a roller radius. And as I said, these equations can be obtained using the force balance equation if you are interested, and you can just derive it. But I will not ask you to derive it. You can just know if there's a need, and you can just use these three equations to calculate the P. But that's not. But if you are very curious, how these three equations are obtained, and do it from the force balance equation, and you will get it. Right? Remember, and there is a plastic deformation. When this is the what is the plastic deformation? The yield, okay? The yield strength. The yield strength at that time is equals this Fy, Fys. This is the yield strength. And the pressure distribution in the rolling. So this is entry, so this is exit, so this is the length between the entry and exit, and this is rolling condition. And based on different frictional coefficient, and you will have different, and this is the pressure distribution. So here is a normalized pressure distribution. Rho divided by Y. Y is a yield strength. So here is the pressure distribution in a yield gap as a function of reduction in the thickness. So this is the reduction. Okay, so here is for the different friction coefficient. Here is the reduction, and you want. This is the rolling direction, and also this is the normalized pressure and normalized value. The pressure over is the yield strength. So here is a determination of the neutral point. What is the neutral point? So here is the definition. Okay, neutral point for this rolling, and to the left of this point, the roller moves faster than the workpiece, and to the right, the roller moves faster than the roll. Be very careful. Neutral point. Neutral axis. We know neutral axis, right? Neutral axis when we solve the beam problem, when we have a bending problem for the beam, and we have neutral axis. Neutral axis means that along this axis, when you bend it, before you and after you bend it along this axis, the length does not change. The neutral axis. Here, neutral point. Neutral point is, it's not analogous, but it's kind of similar. Neutral point here is that to the left of the point, the roller moves faster than the workpiece. To the right of the point, the workpiece moves faster than the roll. That's at that point, these two guys move at the same speed, the neutral axis. So here is how to calculate the neutral axis by equating these two equations. So neutral axis and using this equation. Right? So as I said, you don't need to memorize it. If neutral axis, because our homework and also our exam is a take home. If you see neutral axis, you can just come here and do something. Right? Right? Good. Just know. Okay, Valdemar has taught us about neutral axis. I know how to calculate. I know where the solution, where the equations are. That will be good enough. I'm not asking you guys to memorize it. Right? So here's the front and the back tension. So here, depending on the relative magnitude of tensile stress applied, the neutral point may shift. The neutral point may shift. And this shift then affects the pressure distribution, torque, and the power requirement in rolling. It depends on the relative magnitude of tensile stresses applied. Tensile stresses applied. Tensile stress, you pull it. How big you pull? How big force you apply to pull it? And so this is what this figure says. So calculating these root forces. And how to do it? Calculating root forces, we still use the Newton's law. And we do the, this is F, the rolling force. Rolling force F called the rolling separation force on the strip is the product of the area and the pressure versus contact length curve and is the strip width W. So then you just do these two integrations and then calculate. Calculate the with this is the rolling force. W is a strip width, how wide it is. W. P is the pressure. R is the radius of the roller. The roll torque and the power, and we use this. This is the torque. Entry zone and minus this is exit zone. So this is torque can be calculated using this equation. We know the power required per row is using this equation. So the power, if we change the kilowatts, if we using horsepower, or we use this. In the hot rolling, we introduce average spin rate on Epsilon. So using this equation, H0 is the initial height, HF is the final height, VR is the rolling speed of this is the roller, L is the length. And then we call this row the bending. See? This is roller. Okay, if this row and this row is long enough, if we have a block here and one piece here, is a strip thicker at the center. So we know that because the action and reaction, and finally, and so we will have this kind of final product, for which the strip thicker as this is the center. So this is thicker, and here at the two edges it is thinner. So here for this one, see, some people, they are very smart, okay? So they just adjust, they just change the profile of these two rows and make sure, even though these two guys, and they are deflecting so substantially, but still at the very last, finally they can get, this is a very flat. This is a wood-piece surface. Ground width chamber produce a sheet of uniform thickness during rolling. So threading, it is another word, threading, and rolling plates and sheets with high strip width to thickness ratio. Width and thickness ratio. If the width and thickness ratio is very high, and it's necessary process of plane string. Plane string is width, okay? Width and thickness. That means it is wider. This plane string is a necessary process of plane string. We can just treat it as a plane string, the 2D. However, at a smaller ratio, and such as in a rolling a square cross section, this is kind of interesting. The width increases considerably during rolling and known as the threading. Threading is on the two sides, is threading. Right? So it can be shown that the threading decreases with the following conditions. First one, if we increase the width to thickness ratio of the anterior material, that means make it wider, itself already wider. And second one, and decrease the friction, if the friction is smaller. And third one is increasing ratio of row radius to the strip thickness. So here is several ways for the threading, and also one technique of preventing spreading is by using a pair of vertical rows that constrain the edge of the product being rolled. So this is called Eiger mill. So you need to use two other vertical rows to constrain the edge of the product. This is called spreading. You know, this is spreading. Spreading means when you roll some workpiece that is close to the square, right? The square means that thickness and width are almost comparable. They are comparable. If this is the case, it's definitely when you compress it, and it will spread in another direction, right? So this is called spreading. Make sense? The defects in rolling. There's some the defects. The first one is called we have this rolling direction over here, wavy edges. And so this edge, supposedly we want, if we draw it, and we want these two edge, right? So suppose I want to draw this workpiece. I want this edge and this edge, both of them are very straight. However, for some reason, see, this edge is not straight. It is curved. And also here, it's also curved. This is definitely is change the final shape of your final product. This is not good. So the second one is the cracks in the center of the strip. Here. Okay? So third one is edge cracks. Edge cracks here on both of these two sides, two edges. And D is alligator's mouth open. It is the mode 1 is crack. This is open. Alligator. This is the four commonly seen defects in rolling. One is wavy edges. Second one is liver cracks in the center of the strip. And third one is edge crack on both sides. And the fourth one is the opening, mode 1, the cracking, the opening that we call very, very intuitively, and this is called alligator. So this alligator's mouth, right? And residual stress. And so you can see the residual stress is a very, very important topic for the manufacturing. So when we manufacture something, when we make some work on this the raw material, and definitely we will get some residual stresses. So here, residual stress. So this is a small row and a small reduction in thickness. Suppose. So this is the initial height, and here is the final height. So we will have this is kind of residual stress. And this is tension. On this side is tension. On this side is compression. For here, B is larger row and or large reduction in thickness. Or large reduction in thickness. So we have this tension, also this tension, and this compression. The last time I told you, in terms of particular life, and what kind of residual stress is good, and what kind of residual stress is bad. And somebody, okay, well, yeah, compressive residual stress is good. Because compressive residual stress is always prevent the cracks from initiating and from propagating. Because you press it, there's an internal force to prevent the crack from initiating and propagating. The tensile residual stress is bad because tensile residual stress is always facilitating the cracks initiation and cracks propagation. Vibration and chatter and in rolling. Okay, so vibration. So this is another topic. This is another very, very important research topic. Vibration and chatter in rolling. So in the machining, my research focus is on how if we my research focus in my research I just assume there is no vibration, no chatter in the machining. But some other researchers, and we just focus on if there is vibration and there is chatter, and how this vibration and chatter affects the machining. So here, vibration and chatter in rolling, definitely this is a phenomenon, commonly seen phenomenon. Vibration and chatter in rolling are very, very important. This affects the stability of your the rolling system. So there are some researchers are focusing on this vibration and chatter in rolling, and some also are other researchers, and they are focusing on just assume there is no vibration, no chatter, just to see if how the different material, how the different rolling parameters affects the final performance of final product. Right, so this is very similar to the machining. So here are different several chatters: the torsional chatter, and third octave chatter, and the fifth octave chatter. And you can just take a look. There is a there's a lot of text here. So this is the maybe after you enter the graduate school, if you are focusing on this kind of research, and you need to look into this one more carefully. Okay? But this is out of my research scope. Any questions? You can just take a look at what's torsional. The chatter. What is the chatter? It's vibration, right? If the roller is vibrating, for me, when I just machine something using the lathe, when the lathe is vibrating, definitely it will affect the performance of the lathe and kind of the dimensional final dimensions of my product. Right? Here is the same thing. We just see first we assume there's no chatter, no vibration for the machine, rolling machine, and then we just get the final products. However, actually it is vibration and chatter, and how this vibration and chatter in rolling to affect your final production, your final dimensions, and also microstructure of your final products. So this is very, very important, also very interesting. This is the research area, damping. So you can incorporate the damping. You can just incorporate damping to minimize the vibration and chatter. So roller leveling. So this is a roller leveling. So a flatter. These are rollers. There are many rollers here. So here is a flattened rolled the sheets. There are so many rollers. This is the raw material. This is the final product. So here is a straightened round bar, round rod. This is a round rod. So here is the two rollers. They are arranged in this. They are in the same direction, but these they are in the same but different directions from here. So this has this rod. It's called layering, roller layering. The roll arrangements. So this is more complicated. So we have multiple rollers here. So here is a tool. This is what we see when we talk about this one. Here is multiple one, okay? And you have two directions. This go in one direction, this one goes in another direction. So you can have roll these two sheets simultaneously. Here is another one. So this is two high mill. So this is Dr. Eric Malik is expert here for this milling. So this is 3 high mill, and this is C. This C is 4 high mill, 1, 2, 3, 4, and D is tandem rolling. This is one pair, first pair, second pair, and third pair, and with the 3 stands. So E is the planetary mill. Planetary, just like the planetary mill. It's very, very awesome. So F is a cluster. So this is cluster mill. This is very, very awesome. If you have a chance, just take a look. Okay, so maybe in the internship, when you get the internship in the rolling the companies, and you can go there to look at their very, very awesome improvement. And then we talk about shape rolling. Shape rolling means that we have some this is shape. This is we want to have want to have the final products that have predefined the shapes. So is a blooming rose. You can have almost this I beam used in the engineering. So this edging row, we can have this. This is the rubbing horizontal and vertical rows. Vertical rows there. And so here is the intermediate horizontal and vertical rows. This is vertical and this is horizontal. So these edging rows, see, it is very similar to the I-beam. So here is the finishing horizontal and vertical rows. This is I-beam. This is actually very close I-beam. The room rolling. So room, this is room, as the name suggests. For this room, this workpiece, and we have this is a running row, and so this idler row. So this is the main row. This is driven. So this guy is driving this is workpiece to be rolling. And so we put the force here, this idler row, and you can get this is the product. The thread rolling. Is a thread. The thread rolling process A and B. So heat this one and this, and we want to get these threads. Okay, so we want to get thread. We see percolating the flat dice. We see percolating flat dice right here. So this is the C is a 2-row dice. The moving cylindrical die. So the stationary cylindrical die is a workpiece. This work rest and this workpiece. We want to get this is a thread. The force is applied here. So the last one is task manufacturing. Last one is thread rolled parts. Thread rolled parts here. And made economically and at a high production rates. So this is very awesome and highly sophisticated. This is the thread rolling equipment. The thread microstructure. So here, after threading, we can see. So this is for A is for the thread schematic illustration of thread features here. So B is a green flow lines in machine if we machine it. Okay, if we machine it. But roll the threads, we can see if we get these threads by rolling, and we will see if we use the micro SEM or other these fantastic this is inspection the tools. Or we can see this is our root this thread. This is the greens. But this definitely this one is different. Why? Because here the pressure. Okay, this is you have a higher pressure to have plastic deformation. But this one is machining is just a material removal. The last one is management process. Management process. So here, first one is this is a void. This is a void initiation. Also here, if there is a tensile stress, and it will the crack will propagate. Crack developing a solid round bar and due to secondary tensile stress. So this tensile stress, if you press it, it goes this way. Right? This is the tensile stress. So here is a simulation of a rotary tube piercing process. This is a tube. We want this cavity here. We have this cavity. We want to get this cavity here. C is the management process. This is a mill. So we have a solid rod. This is which is a material workpiece, and we have a tube manual. This tube manual stays here. So these are rows, and finally we'll get a tube. So this is for seamless tube making. This is the very interesting one. If you have a chance to visit some company or some factories, if they have this kind of rolling machines, and go there, okay, to look at how they do the rolling work. Any questions? Everyone? No question? Okay. So if there's no question, so I hope you can attend the the office hour, Monday, Wednesday, Friday. Okay? So if you have some modeling problems, you can share your screen with me, and it is much easier for me to figure out what your problems are. So,
And I know it's Monday, Wednesday, Friday, but what's the time?
4 to 5.
Okay.
Yeah, 4 to 5. Right? So,
Is the homework due Friday or is it due Monday?
To Monday.
Monday.
5 p.m.
Monday, okay.
yeah, because this Friday is the
Mental health day.
mental health day.
Yep.
Okay, great. So, both undergraduate students and graduate students took class, right? Is that right? Or just for the undergraduate?
I think it's just undergrad. I'm not sure. I think it might be for everyone except the law students. Why men?
Oh, okay. I'll double check.
Yeah.
Great, thank you.
Yeah.